Hey everybody, if you're just logging in, we'll be with you guys in just a few minutes. So sit back, relax, and we'll be with you in just a moment. If anybody has any questions or anything they want answered at the end of the show, please go ahead and feel free to go ahead and type it all out in the comments section. If you're on YouTube, feel free to go ahead and type your questions into the comments section. And of course, if you're in StreamYard, that should be to your right. You can go ahead and type in any questions, and we will get those answered for you guys at the end of the show. Seeing some comments pop up. John, Rick, Jackson, welcome. Good afternoon to you guys as well. And again, if you're just now tuning in, we will go live in 2 minutes. Hey, everybody, and thank you for tuning in to another live episode here at Hero Appliance Academy. We do have a special guest with us today, and we'll get into everything to finally finish the series on learning basic wiring schematic. Like always, I'm JR, Director of Technical Development here at Hero Appliance Academy. A little bit of background of me. I've been in the service field for about 15 years. I started in property management before going into the appliance field about 5 to 6 years ago, and worked at Whirlpool in the tech line department. And now I'm here doing training at Hero. And I want to introduce our guest here. This is Ben. Go ahead, Ben.
Hey guys, my name is Ben. I started in property management roughly 6 years ago. I had been doing appliance repair for roughly 2 years while I started with Sears. I had a good opportunity to come to S&S Appliance to better my knowledge and learn how to diagnose things better. And I have learned greatly with JR here, and I'm very grateful for this opportunity to be here.
It's great to have Ben here. He's going to be helping out on today's show and kind of demonstrating and giving some feedback of what it's like here at Hero Academy. So before we get into it and we finish, this series into the wiring schematics, we're going into part 3 now, and we've kind of talked a lot about, how to read the schematics, and we're going to kind of tie everything together and hopefully end this series before we move on. But before we get started with all that, it is going to be time to do our tool of the month recommendation. We do have it right here. Let me get all this out. And the tool of the month is going to be the Klein's tool. This is going to be the 1/4 inch to 5/16 bit. We're all familiar with the Malco, standard Malco 1/4 inch and 5/16. Klein has something similar to the Malco. This is the original Klein tools. And I know this is kind of small and kind of difficult for y'all to see, but this is the original Klein tools, 1/4 inch and 5/16. It was great. The problem with it was, of course, you had a very longer shaft on the bit itself, and also if you wanted to put a bit on it, an actual driver bit, it kind of would just come right off. It really kind of see. It kind of just wiggles around, doesn't really hold in place. Overall, it was okay. Now, Klein has kind of seen what the Malco has been, doing, and Malco has been okay. That's pretty much been the industry standard, what I've seen most guys in HVAC field using the Malco 1/4 inch to the 5/16. You could place a bit on it, but your bit would also move quite a bit. And it could even, come off. What's happened with the new Klein is we've gone down to a 3-inch shaft. You could try to get you guys to see that. So we're on a 3-inch shaft now. Still got the 1/4 inch and 5/16. But what's also good that Klein has done, and kind of see it right here. There we go. And what Klein has done is they've given you the option to you kind of push it out. You do get a symbol in the middle for a bit holder, and you can actually attach a bit, and now it will hold magnetically, of course, a bit to that, and you still get your 1/4 inch and 5/16 on that 3-inch shaft. Of course, everything that Klein has been doing, it's impact rated, so you don't have to worry about breaking it or anything like that. Now, we have been putting it to the test.
Yep.
We've been putting this shaft through the test. We've done a full gear case replacement with using this shaft by using the 10 millimeter and the 13 millimeter sockets that Klein also makes that will go onto these shafts. These are pretty much universal Klein shafts here. Then they also offer sockets that will fit in here. But we have been putting them to the test. We've done a full gear case. Really torquing down that gear case, 10 millimeter on our motor drive, 13 millimeters on our motor drives and our pulleys. We have seen no cracking, no twisting of the shaft, nothing like that. So this is going to prevent you from having to take the bit off. So if I was on my drill here, and of course I'm doing my standard 1/4 inch and 5/16, if I wanted to get a bit holder or add a Phillips or a flathead, I would have to take this off and get a Phillips attachment, number 2 Phillips, or get my flathead on there. What Klein has done, of course, is they've let me keep my attachment, and all I got to do is lift up on the actual socket attachment and drop my bit in, and there's no wiggle room. I mean, it is solid on there. This point, I'm not having to take the actual bit off and use another bit. This has been, one of my favorite tools. You always keep it, you always keep your drills loaded. You know, that's pretty much what you're walking into the house with, 1/4 inch, 5/16, but now you have the option to add a bit to that attachment, which is, you know, going to save you from having to take it off. Klein has been really good with, you know, providing tools, multi-purpose tools, so you don't have to carry as many tools in your bag. So been really happy with this, and we'll throw, of course, the part number. There's a part number, as you can see. This is considered by Klein a 3-in-1 instead of the Malco 2-in-1 with the 1/4 inch and 5/16. Of course, we all use the Malcos. They're great, phenomenal tool, but they limited you to a 2-in-1, where now Klein is giving you a 3-in-1 with a bit holder. So absolutely great. And we'll throw a link in the comment section for you guys as well. You should see the link there if you wanted to grab it on Amazon. That is not an affiliate link. We are not trying to do that. It is on there for you guys just if you're interested. I think they're running roughly right now about $10 for this tool. They were on sale not too long ago for like $7. So great tool to have, really phenomenal.
Saves time and takes the hassle out of it.
Yeah, absolutely. Absolutely. Really does. And, you know, Ben can speak to it because we have been really pushing these tools through the test on what we do every day as appliance technicians when we're really torquing things down. And I've even put this to the test when taking the agitator bolts off, which, you know, sometimes your standard impact might not even be strong enough to take that agitator bolt. The Klein Tools shafts, we have a longer shaft for this. It also has been able to withstand that as well on a larger impact. So really a great tool. And that's going to be our feature tool of the month. So if you're interested, it should be in the link, and you can grab it there in the comment sections. And let us know feedback. If you like it, don't like it. And if you have any recommendations yourself, do you have a particular tool that you love and that you use every day that you want the world to know about? Please feel free to send us a link. We will put the tool to the test ourselves. And if it makes the cut, we will make it the tool of the month. So make sure you are sending that, and you can email that to us. We'll throw our email up there for you guys to see. You can email us questions, recommendations, anything like that. You should see it on your screen right now. Shoot us an email, and we will look into it ourselves. All right. So ready to get into the show?
Yes,
we are going to get into the show for today. We're going to jump in here in just a second into the computer, but what we're going to talk about today, I'm going to give you all a brief overview. We're going to be talking about a dryer, and you can see it's in the back here, the model number that we're talking about, the 4950 Whiskey Echo Delta 4950 is what we're going to be talking about. We're going to be using the schematic to do some of the basic checks that we would do, everything from the console, even down to ohming out our motor circuit and actually checking the motor windings from the timer, which is, I will tell y'all right now, it's a more advanced type of calculations that you need to do. And we'll talk about that, why you need to do certain calculations to ohm out parallel circuits. We're going to show you guys how to do that. Everything, again, from the timer. So let's jump into the presentation here, and we will get into it. All right, so right now you should be seeing my screen here for the presentation of today. Again, this is on the Whiskey Echo Delta 4950 Whirlpool dryer. This is considered a top-load dryer. The reason we say top-load dryer is because our console is on the top of the dryer. This is pretty typical when you see, of course, your lint screen right here on the front. This is considered a top-load dryer. No, there is no such true thing as a top-load dryer because we always load our dryer from the front. But dryers are considered front-loading or top-loading based on the console position. So this is considered a top-load dryer. If the console was right here on the front, as you can see here, that would be a front-load dryer. All right, so let's get into it here. There we go. All right, so this is the schematic for this dryer. It's very standard timer-style schematic. One of the things I really want to talk about is we talked about permanent connections and terminal connections, knowing when you have a splice in the wire and where those are connections that you can undo or check power at. So again, we talked about black dots. When you're talking about black dots on a wiring schematic, that is a permanent connection. That could be a splice, a manufacturer splice, or it could be, a wire split off or anything like that. That is something the manufacturer has made permanent. That means you cannot undo these wires. Technically, yes, you could undo them, but you're going to be cutting a manufacturer splice, and you're going to have to resplice that up yourself. But that is, technically speaking, a permanent connection. These white dots right here, what you see, these white dots are always terminal connections. That means that we're allowed to disconnect the wire from the component, and we can also get to this connection to make a voltage check, whatever it may be, with our meter leads. So everything you see here, over here in our door switch, you can see the door switch has multiple terminal connections that we can actually get to, disconnect it, or check power to it. Over here on the motor, you can see the motor right here. We have terminal connections. These connections are, again, something we can check power to and or disconnect. At our centrifugal switch, and then you can see in wiring harnesses, permanent connections. Then we have right here off of our L2 line, we have a permanent connection that is going straight over to our timer motor. That is going to be, again, permanent connections. So the reason I bring this up is, one, we're going to talk about how the circuit's all flowing, but also talk about the importance of understanding, timer charts and how to read the timer charts. When you look at a schematic like this without actually traced out, and we'll show you what it looks like traced out, but when it's not traced out, you kind of get confused with all these little kind of breaks in the line. We talked about our source and our paths and our loads, our switches, the things that make up your wiring schematic, just like like a road map where you would have road names and signs and different things like that, highways, so you would know where you're going and where you are. Well, the same thing is happening here, but of course we have a lot of breaks in this wiring schematic, and what these little C, H, B, and A, what do these letters mean? That's going to be different than these words like red, LBU, which is light blue, R for red. Those are not actual timer contacts. Those are the color of the wires. So R for red, and you can see you kind of have R here for red, and then you have the word red spelled out here. Manufacturers are going to do that to you. Sometimes they might spell the whole color out for you. They might use abbreviations. So just keep that in mind. We do have R for red, RW for red, white. That usually means there's a tracer, meaning the wire might be a solid red wire with a white line down the wire. That will let you know that there's two colors to that wire. That will be a tracer. And of course, what that means related to this chart. Because if you look right here on this chart, you can kind of see those contacts. You have T and X, TF, CH, CB, CA, and so forth. Those are the same contacts you have in your wiring schematic. And the importance of it is to actually know, and let me just kind of clarify a little bit. You're only going to be dealing with this when you're dealing with timer-styled appliances. When you have a timer, you have different contacts, and the technician has to be able to understand or know how to read the schematic based on when timers contacts are closing, when they're opening, so you can make your checks. Because if you don't know when something's open or closed, you don't know what the result is going to be. And that's what this timer chart is telling you. You have a white square. As you can see, you have white square kind of throughout this chart here. That means an open contact. The lined square, that is a closed contact. A black solid square, that means it doesn't matter. It could be open, could be closed. Then you have the one with the circle and the O in the middle, or zero, how some people say. That means either, but not both. That means one of those contacts is going to be closed, but not both. As you can see, the only place we see that is right here on the cool down, where T and X or T and F, one of those can be closed, but not both at the same time. The only way for you to find out is to pull the meter out and check yourself. And then you have the plus sign for an intermittently closed contact. So that is kind of just how to read this wiring schematic and understand it. So let's go into tracing it, and let's see what it actually looks like when we actually have everything running. All right, so right here, we have a full system. This is a fully operational dryer with everything traced out. We're using blue for our line 1. We are using yellow for our neutral and our red for L2. And as you can see, we have our neutral coming through the circuit to one side of the push to start relay. Now this is showing you the schematic. It's showing the schematic as the push to start relay has been pushed and the unit is running. You can see these little arrows right here telling you that the motor is running, the timer motor is running, and that's what it's kind of written out and traced out as a fully functional unit with the heater running itself. So you can kind of see, again, understanding these contacts, and we do have it on a timed regular cycle, so you can see C to B. We have, we have electrical current flowing through that, and if we come here, C and B on timed regular, we have a lined square. That means it's closed, which of course explains it. So we are closed, and we are feeding down to our motor. C, B, and A are closed. So again, right back to C and B, because you got to be C and B and then B to A. So you got C to A and C to B. There is no C, there is no B to A because you can't close C to A without closing B. So you got to kind of just go C to A and then C to B. All right. So this is what it looks like. Current's flowing. We have some back feed here. Our L1 gets to one side of our heater, but it's also back feeding to our F contact on our timer. Going to show you some failure points and how to use the F contact, the orange wire, to your advantage here. So we're going to kind of get into it here. All right. So this is looking at a timed regular cycle with an open neutral to our motor. Now the open neutral could be an open, broken wire, or bad door switch, or whatever it may be. On this situation here, we actually bugged our dryer to have an open contact on the timer. And the reason I did this, I did have a call not so long ago from a technician who had an open contact on his timer on the neutral side to the motor. After the motor had been replaced, still couldn't get it to run. We find out that we had a open contact, and I showed the technician how to do that, and we're going to kind of talk about that. But before we do that, let's talk about how to understand this motor winding situation here and how we could check these motor windings without taking the unit apart. Because we all know, most technicians, when you're going to check the windings on a dryer motor, you're pretty much disassembling the dryer, get into the motor connections, you're pulling the copper lines off of the contacts, and you're ohming each winding individually. There's a way to actually do it from the timer without having to take the whole unit apart. We're actually going to ohm out this motor and see if these windings are within range. So our main winding says 2.4 to 3.6, so anywhere between those. 2.4 to 3.8 on our start winding. So you have a main winding and a start winding here for your motor. And they're wired in parallel. These are not series circuits. This is a parallel circuit when it comes to these motor windings. They're wired in parallel. When things are wired in parallel, you can't just add the windings together and get your numbers. Like in this scenario here, let's say 3.8 to 3.6. If it was a series circuit, we would just add those up and get, I think it's like 7.4, I think is what me and Ben did earlier, roughly around 7.4 ohms if it was a series circuit. When we're talking about parallel circuits, you actually have to follow an equation rule to come up with what that motor winding is going to be. And you'll be shocked to know what it's going to be when they're actually wired in parallel. So what we're going to do is we're going to jump over here to the whiteboard, and let me just kind of highlight this area that we're talking about right here. Again, you guys should be seeing that 2.4 to 3.8, and then we're looking at 2.4 to 3.6. We're going to be using the higher side. You always start with the higher side of the ohm resistance value that the manufacturer's given you. So if they're giving me 2.4 to 3.8, I'm going to go to 3.8, and I'm going to use that. And I'm also going to use my 3.6 main winding value. So let's go over here to our whiteboard. All right, so let me show you guys here the equation at the top. So what y'all should be able to see is resistance equals 1 over R1 plus 1 over R2. And what that means is resistance value number 1 and resistance value number 2. So we're going to do this math together. So we know we got 3.6 and 3.8. So all you got to do is, once you learn that there's an equation out there, all you're doing is inputting numbers and adding and doing your divisions. That's really, really simple, all you're doing. So in this case, we're going to be looking at R equals 1 over 3.6 plus 1 over 3.8. Those are our resistance value that we're just inputting into our equation. So all we're going to do next is we're going to divide 1 by 3.6. So we're really going to be looking at 1 over, I believe it's 0.27. That would be 1 divided by 3.6. You feel free to do the math. We've been doing this math all day, so I kind of memorized it by now. And then we're going to add that to 1 divided by 3.8, which is our other winding, which is going to be 0.26. Now we're going to add our lower number, which is going to give us 1 over 0.53. And at this point, we now divide 1 by the 0.3, which gives us 1.88. So that is the resistance value we're looking at. We're looking at R equals 1.88. This is, again, what we talked about. This is way more advanced. Ben's going through training here, so we're kind of looking at, this is the only way to calculate a parallel circuit for you to measure the winding, especially when you're dealing with something like this. You're going to have to do the full equation to know what your resistance is. It's a little bit different than your series circuit, because in your series circuit, all you would do is just add 3.6 to 3.8, and you would have your resistance total. But on a parallel circuit, you have to go through the equation so you can get to 1.88. Usually you'll round up to like 1.9. And also this is going to be dependent if the motor's been running. So the resistance value might be, a little bit off. You're always going to be within plus or minus 5%. Usually roughly about there. So I would be anywhere between 1.6 to 1.9. I'd be happy with that motor. Anything away from that will be a problem. So let's go and let's see what we're going to get. Are we going to get 1.8 at our timer to our motor winding? Let's go back here and let's take a look. So let's jump to the computer here and let's talk about where we're going to measure this. Again, like we said, we are now going to be looking. Let me find my mouse here. All right, let me switch to my laser pointer. There we go. All right, so we know our equation has given us 1.88. But where are we going to measure this? All we have access to is our console. We don't have access to our motor. So how are we going to do this? What we're doing is we're looking at our nearest points of contact. So if we look at our motor here, nearest point of contact on our timer, if we follow the neutral side of the motor, it's going to be right here on S. The S contact should have a white wire. There's a permanent connection here in the harness, but we should have a white wire on the S contact of our timer. So there's one of our test points. This is going to give us, and if you follow this, you'll see, trace it all the way over here. It makes contact with both our start and main windings. And then the other side, right here on our 4M, the nearest point, if we follow it, is going to be our push to start relay. Again, that's in the console. So that will be the other side of the circuit. So we should be able to test from right here on our push to start relay and right here on our timer for the full circuit, and we should get 1.8. And that's what we're looking for. We're looking for 1.8, well, 1.8 ohms, and that is including our start and main windings together. So let's actually talk about it on the unit. We're going to have Ben here display this for you guys. So let's talk about it on where it's at. So if you want to come in here, Tommy, and take a closer look, here's our S contact. You can see S, here's our white wire. All right, now we come over here to our star switch. We got to find our blue wire. And this is where things get complicated because you got two blue wires. How do I know which one's going to the motor and which one's going to the timer? Because we need the one that's going to the motor. So what you do is you come into the main harness and you'll see that you have a blue wire going down to the motor. And all you do is if you pull on it, you'll see that you're pulling on another one. Then you kind of follow it. All right, I'm pulling on this one. If I pull up, I'm pulling on here and I chase it. There's the blue wire going to my motor. That's as easy as it gets. You kind of just start from one side, pull on the wire, and then you kind of just follow where you're pulling until you get to your point of contact. So here's that blue wire on our star switch that we talked about. Here's that white wire on our timer that we talked about. And let's see what we get. Go ahead, Ben. Show them. Hopefully we're not crazy. And look at that. Wow. 1.8 ohms.
Right on the money.
Right on the money. So right there, and again, 1.7. If I was to run this dryer, I probably would get like 1.9 once the motor heated up. That's a parallel circuit. So I'm testing the full circuit. So I could test my motor windings without taking my dryer apart, without having to get into anything crazy. I can actually ohm out my motor windings right here from the console assembly. As you can see, the hardest part of doing this is that you have to do the equation. All right, let's come back over here to the desk. All right, and like I said, it's not about, the hardest part is not doing the equation. The hardest part is remembering that there's an equation out there. As long as you know the equation itself, it's just inputting numbers. You know, Ben kind of saw it, you know, through training. It's something that just needs to be in the back of your head. So if you guys want to, you know, kind of screenshot of this, again, it's going to be back on YouTube. We're going to post this on YouTube. So you can always go back to it. Again, we got it, our handle there. So you can go back to it and rewatch it if you missed it, or if you want to kind of refresh on what that equation looks like, because you can use it on any and every single thing that you do, even if there's more than two. So our equation was designed for two loads on a parallel. If there was 3 or 4, even 5, I mean, me and Ben have done it. If there's multiple parallel circuits, all you're doing is, you know, like you saw in the original one, R1, R2, R3, R4, and as long as you have the resistance value for each load, you're just inputting those numbers in, you know, divide, just simple division, adding, and of course we all have phones. Pull the calculator out. That's going to be a lot faster than taking the whole dryer apart, getting to the motor, and then checking the motor windings, where I can do the math problem while I'm here on the console, take it all apart, and you'll be surprised on the feedback you're going to get from your customer when they see you do something like that and realize that you can test their unit without taking it apart. I mean, that is a level of professionalism and knowledge on their appliance, and they're going to recognize that right away. All right, so let's go back here to the computer, and let's talk about some other things that we're going to be testing here, improving on our unit. All right, so again, this is going to be an open neutral. This is what we were talking about before. We're talking about an open neutral, and that's going to be our T2 and our S contact. They're open, so we can't flow. That's what you're seeing. That L1, the L1 isn't going to stop at the motor. It is going to backfeed through the windings, because electricity is going to flow until there's an open circuit where the resistance is too high. You got infinite resistance, and the electricity just can't flow. We can't flow current through. So motor winding is not going to stop our L1 from flowing through our circuit until it reaches the first open, which is our T2 to S contact. So what would that voltage look like while it's running, when it's a good close contact, and what it's open? When it's open, you should read 120 volts, right? As you can see here with it traced out, you have L1 on one side, you have neutral on the other. That should be 120 volts. But if you had a properly working unit, this neutral would feed all the way through to one side of the motor. So if you went across T2 and S with a properly closed switch, you would read 0 volts, and that's due to you reading the same side of line. There's no potential difference between those 2 points. And when we deal with electrical currents and electrical systems and circuits, we deal in potentials, potential difference between 2 points. So let's prove this on our unit here. Let's go back to our unit. All right, so that T2 and S, we're going right back to that white wire that we were at before, and this is our T2. So this contact right here, this is where we would read 0 volts if it was closed. In a closed state and our motor was running, we would get 0 volts. But if it's an open state, we have neutral on one side, line on the other, we will read 20. So let's go ahead and run this unit. Hold on. Let me put it on time dry. There we go.
All right.
Let's start her up. All right, we have a functioning unit. The motor is running. Go ahead and read voltage there for us. So, as you can see, we are on VAC. Now we are only on 50 amps, but that's fine. We can come over here to the bigger one. That's fine. We're only getting, you're seeing 0 volts there. And you can see where, go ahead and move your hand over, put your meter leads back in there, and just move your hand out of the way so they can see. You're fine. All right. As you can see, we're in there. We're making contact, and we're getting 0 volts across that contact because there's no potential difference. But we are flowing current. We are still flowing through the circuit, and you can kind of see that. We're just doing our neutral circuit side, so of course there's going to be no difference between the 2 to ground, as you see there, because this is our neutral side of our circuit. You're not going to see anything. But let's go ahead and kind of show you guys if this timer contact was bad. Let me get everything here. All right, Ben, and you can kind of put them in there and hold them for me.
All right.
All right. Now we're going to we got this unit bugged in a way that we can kind of show here. All right, now we're going to kind of show you guys. I believe on this unit, you do have to have it running. All right, we got it running. We're seeing the 0. Now we have an open contact. We're still in the same circuit. You saw how it went from 0, but as soon as the motor shut off, because we broke neutral, to our circuit, now we got L1 on one side and neutral on the other. And that's how you would test this circuit. A lot of guys want to come over here and they want to test with continuity, and they want to check continuity. One thing I hate about continuity is continuity will lie to you once you have a load on the wire. If you have a wiring issue, a pinched wire, any type of issues with the load, what you might encounter is that wire might not be able to hold the current, and it will drop out under load. So that's the problem with continuity. It will test good under continuity, but as soon as you put power to it, it could drop down. So I always recommend checking voltage. Voltage will never lie. Electricity does not lie to you. So as you can see, we have an open circuit, and because it's an open circuit, we got L1 on one side, neutral on the other. All right, let's go ahead and you can go ahead and pull the meter leads out, and let's shut her off. And let's go back. Let's go back here to our computer, and let's look at a couple other failed points. All right. So this is a fully functioning unit with the push to start not engaged. So you can see our neutral now is now back feeding through our motor, all the way back to our push-to-start switch. So we have L1 on one side of our push-to-start switch. We have neutral on the other. Pretty much this unit's ready to go. As soon as you hit start, the unit should run. But how do you test this push-to-start switch? So the first thing to do is understand which light blue is going to the motor and which one's going to the timer. You can see this light blue here will go to the B contact. We have those black dots. Those black dots mean permanent connections. So we have a terminal connection on the push to start relay, and we're back feeding it all the way through our timer. The other side, we have that light blue wire all the way to our motor. And then we have neutral on the other side of our relay as well. So what's going to happen is once we push this, our line voltage is going to come down and go straight to our motor. Our neutral is going to be pushed back to the other side of our relay, and we can check voltage across our relay and across our start switch. And we're going to kind of show you guys what that looks like and how to use a schematic to check that. Let's go to our unit. All right, so we're back at our unit here, and we're going to focus on our push to start switch here. And of course, we've already talked about how to figure out which one's which, right? Start down here, kind of start tugging on wires. You'll start seeing them move, and you know which one's which. So of course, we're going to cross our blue wires, and as we saw with this unit, you got to close the contacts. Once the contacts are closed, you can see our timer is running. We have neutral on one side, and we have power on the other coming from our timer. What's that going to look like? Show them, Ben. So we got 120. If you want to show right here on the switch, we have 120, and we're checking across the two blues. Now, what's going to happen once we close the switch? Once we push the switch in, we're going to send power from one light blue to the other. That means that there is no more neutral. There's no potential difference. What's going to happen, Ben, if there's no potential difference? What are you going to read?
0.
You're going to read 0 volts because there's 0 potential. Let's go ahead and start her and look at our. Go ahead and look at our meter here, and let's hit start. Look at that.
0.
We're dropping down to 0 volts, 0 potential. But let's say the motor wasn't running. How would you know that the switch is sending power to the motor? Let's go up here to our switch, and you can see we're going right back. This is the blue wire sending it to the motor. Here's our neutral to that relay like we talked about, the pink with the black. All we're going to do is we're going to stay with the light blue going to the motor, but we're going to move our other lead to neutral. Let's make good contact there. And there we go.
There we go.
Now we have potential difference because we have line and neutral. With us having line and neutral, we now have a potential difference. If the motor wasn't running, but I was getting these readings, it would tell me my start switch is good. There's no issues with my start switch, and that's the way you check it. You check 120 volts to your start switch, you press the switch, and you should drop down to 0 volts, and then you want to check output from your switch through the neutral of the relay, and you would know if you have 120 volts to your motor. So that is the best way to check the start device. A lot of people like to put jumpers and they jump it out. You really don't need to. If you know how to read a schematic and you know how to use your meter, you don't need to use jumpers. You don't need to second guess yourself. You don't have to put yourself in a dangerous situation. Just pull your meter out, make your checks, and it's going to answer your questions.
And you didn't have to tear it down to get to the motor as well.
You didn't have to tear it down. That is the goal. It's about time, saving that time. You don't always have to take something apart to get the answer that you need. All we did was take off the console. That's all we did on this. And imagine being in a customer's home in those situations where you're in a tight closet or those apartment complexes where, this dryer's up against the wall and you got, you have a very small space you're dealing with. You got, the craziest, venting system you've ever seen. You don't want to deal with all that. Drop the console. We owned out our motor. We can check power to our motor. We can do everything we need to do from right here. The only thing that we're bringing in is knowledge on how to read a schematic.
And it's shortened your diagnosing time as well.
Exactly. You shorten down your diagnosis. And, Ben's been seeing, the difference in what that makes.
Right.
So let's go to our final here. situation, and then we will be done and go into our Q&A. And this is going to be a working unit with no heat. Again, we're talking about, checking our closest points. Our closest points on L1 is going to be A. Our closest point for L2, because our heater isn't working, L2 is going to backfeed. Again, it's going to backfeed until it gets to its open side of the circuit. And this is to test to see if our thermal cutoff, operating thermostat, or high limit is open. If any of these are open, these are the measurements we would get. From A to F, we would read 240 volts. If this was a working system, L1 would feed all the way to the heater, then backfeed to F, and we would read 0 volts from F to A. That would be 0 potential difference. Let's look at it on the unit, and let's see what it looks like. All right, we're going to put it on time dry. We are going to go ahead and start our unit. All right, and we're going to that F contact and the A contact. That is going to be this red wire and orange wire. So go ahead there. This is a working system, of course. Now we have it in a failed state. So right now we are reading 210 volts. This unit is not heating. What this is telling us is that we have either an open high limit, open operating thermostat, or a open high limit cutoff. And when I say the other high limit, is we're talking about high limit thermostats. But let's see with the heater working. I'm going to come over here, and I'm just going to, this is a bugged unit. We'll go ahead and switch it to where it heats. So now that our unit's heating, we didn't move. That is the circuit. Again, we're checking the same side of line because now we're back feeding that L1 all the way to the F contact, as we talked about, and we're seeing 0 volts. The unit's now heating. Again, if we had an open side of our circuit, we would read 209 because one of those is open. And that's typically where you would check when you're in the customer's home. If I'm suspecting an open line in my high limit thermostat, my high limit cutoff, my operating thermostat, that's where I would go. My orange F contact and my red A contact, that is going to provide me with the answers I need. Again, this is without taking the unit apart, using the knowledge on how to read a wiring schematic, and you can make these checks. Let's go ahead and shut her off. And go ahead and unplug her there, Ben.
Yes, sir.
And we'll go back to the desk here. All right. So we kind of, again, like I said on the very original part 1 of this series, wiring schematic comes second to understanding electrical theory. Electrical theory is the #1 thing you need to understand first, because if you don't understand electrical theory, you don't understand how current is flowing through a circuit, how backfeed works, and those things. And Ben can speak to that. Ben has been through our classes. And Ben, can you kind of give us feedback on what it's been like coming through the academy?
Yeah, learning how to read the wire diagrams and understanding what it means helps just be a better technician. And like I said earlier, it takes down time on diagnosing things. It makes diagnosing so much easier than, just tearing it apart and trying to trace things that you could just simply find right there underneath the console. And just learn how to use your meter better will help you tremendously as well. JR has taught me a lot here, and I'm very thankful for that. That's going to help me in the field be a lot better and more productive, and get first time completes as well. So
yeah, absolutely. And how's this whole experience been compared to past trainings you've dealt with, and what's the difference of what you've seen in this experience here compared to what you've experienced?
It makes you feel more of a technician and not a parts changer and trying to make educated guesses. It makes your first guess feel more like it's going to be right instead of ordering 2 or 3 parts and just hoping one of them fixes it. So it makes you feel more confident in what you do, makes you more confident, and customers can feel that as well, feel the confidence off you and feel your professionalism with them as well. So it just makes your work day to day a lot better and easier.
Yeah, it's a lot better than coming into a unit and talking to the customer, and you're like, okay, you know what? I'm going to go ahead and order you a timer and a motor, and I'm going to order you a belt switch, and let's see what happens, And then the customer's staring at you going,
Yeah.
Well, what? Or you could show up and you can make those checks, or you could be the third guy, which is the guy that shows up in the customer's home and there's parts everywhere.
Right.
There's nothing crazier than a customer walking in and they walk in and they just see stuff everywhere just for you to find out he got a bad motor.
And like my experience here as well, also I can show them and break it down to them so they can also understand why it broke, because it might have been something they may have did, just didn't know, and next time it can be preventable and might help it last longer.
Communications is it's key. So I appreciate the feedback, Ben.
Yes,
appreciate you being here.
Yep, thank you.
You got another 2 more weeks here with us. He's gone through a laundry week. He's done basic electrical theory into laundry week, and now next week we're going to do cooking and refrigeration. Refrigerators, and then his last week here will be the full seal system week. So now we're going to go into our Q&A for the day, and we will let y'all go afterwards. So let's see what we got here. What can you do if the colors on the wiring diagram don't match what is on the unit?
That happens.
That is going to
happen.
Yeah, it's going to happen. Manufacturers are going to make changes. They could write that schematic for the first million or so units, and then as production changes, they might switch to a different supplier of wiring or whatever it may be, and the colors might change. But the things that you want to look for is that pin connections will never change. So when you're looking at a wiring schematic, if it tells you it's a P1 with 4 pins and it's the 3rd pin on that connector, and let's say it says it's a red wire, it might be a brown wire, but as long as it's that P1 on that 3rd pin, it is going to be the same. And that's sometimes what you have to fight through is the manufacturer might have changed the color, but they're not going to change the pin location and the pin connector on the control. And that's what you want to look at. How do you properly check if a dryer is heating correctly? The best way, there's several different ways that technicians do it. I've seen a lot of techs do internal temperatures. The best way to verify that the dryer is heating properly and within the cycle is you want to check exhaust temps, never inside the dryer, because those can vary depending on the ambient air and so much more. You always want to take exhaust temps. That's using a thermocouple, not a infrared gun or anything like that. You want to use a thermocouple. You want to take the exhaust off of the unit, place your thermocouple in the exhaust, slide your exhaust back on to your output of your dryer, and you should read around 150 to 160 degrees on the high end. And when the unit cycles the heat off, it should cool down to roughly around 120 degrees before cycling back up, and it can come down to 113 or whatever. It all depends on ambient air as well and what's inside the dryer. You're going to get cooler temps with if you got a wet load, or you have no load, you might just be dealing with that 120 to 150, 160 degree. You're going to be cycling between those, so you're going to be seeing that roughly that temperature swing. That's how you know the dryer is doing what it's supposed to do. If the customer has wet clothes in the cycle, it's something else. What is the best meter or leads to use when checking a unit? Ben came in with a different type of meter. And there is meters I'm going to recommend. I like something that stands behind the product. Field Piece, Fluke, those are good meters. They're going to give you good quality. You're going to spend the money on something that's going to make you money. If you get, let me grab something real quick just to show you guys. If you grab a $20 meter, you're going to get $20 results. You're going to get bad leads. They're going to, especially when you're checking thermistors, things that you need proper resistance value, they're going to be way off. This meter right here was $20, and it was reading about 15 degrees off on my thermistors compared to my Field Piece. So really, the best meter to use is a high quality, good grade meter, Field Piece, Fluke. Those are meters I would say are the best. Could you check from the timer if the power coming out of the timer to the heater before thermal cutoff? I had one that the thermal fuse, heater, high limit, and outlet thermostat, all tested okay, but no heat. Well, let me read that one. Could you check from the timer if power coming out of the timer to the heater before the thermal cutoff? Before the thermal cutoff, that was what we just did. So we checked power before the thermal cutoff, right?
Yeah,
That's
yeah.
what we were doing.
Yeah.
And that was, and then your thermal fuse will have nothing to do with heat. Your thermal fuse is purely motor. So your motor was shut off for your thermal fuse. Your high limit outlet thermostat, those are all after. So the check that we just did, it is going to group those three things together. So once you determine that that whole circuit is open, it is going to be pretty much up to you to go down there and figure out one of those three is open. That would mean if I was to get that, what we saw between that A and that F, we had 209 volts.
Right.
This is, of course, three-phase where we're at. We had 209 volts. That's telling me my heater's good. If my heater was bad, then I would have got 0 volts because I would have backfeed my 120 volts. My heater would be open. But because I saw 209, that was telling me either my thermal cutoff, my operating thermostat, or my high limit thermostat was open. You could also have an open wire that would do the same thing, but you would narrow it down to those three. The heater thermal fuse, that would be the thermal cutoff, which is non-resettable. That is what we're talking about. Yeah, that's the heater thermal fuse that is going to be the thermal cutoff, also known as the high limit cutoff as well. All right. So looks like we answered all the questions today. I want to thank everyone for tuning in from YouTube, through StreamYard. Appreciate everyone coming in. What do you want to see on future classes? We do have some things lined up. We're really excited. We're going to get into some dish products, some refrigeration products. Next training is going to be Thursday, the 22nd of this month, and we're going to go into a new series. Now, this finally wraps up our wiring schematic series. This is a 3-part. Again, everything will be on YouTube for you to rewatch. So if you're curious on that parallel circuit equation, this will be the time to go back and look. So again, thanks everyone at YouTube and StreamYard for tuning in, and we will see you guys on the next round.
Yes, sir.